Hello and welcome to this new video. Today we will be presenting a paper that proposes an algorithm to compute the gradient of a logarithm determinant. What does that mean? We will explore it in the next section. The paper was written by Thomas Baker from the Department of Physics at Astronomy at the University of Victoria and James Grizzly from the Department of Chemistry at the same university. The presentation of this paper will be structured as follows. First, we start with the introduction, some definition, and the motivation behind this work. In other words, what the author are trying to achieve. Then we dive deeper into the section on the quantum gradient of the logarithm of the determinant, and examine how the author approached this problem. Next, we look at some of the applications suggested in the article. After that, we discuss an extension of the solution proposed by authors. Finally, we conclude with the paper's conclusions and outlook, and as usual, we will close the video with our own appreciation of the paper. So let's go introduction. So far, a matrix X. So for a matrix X, this quantity represents the derivative of the logarithm of the determinant with respect to the variable x, e.g. And it turned out that this quantity is equal to the inverse of the matrix X. The author points out that the logarithm of the determinant appear in many developments in physics, which make it a very relevant expression. They also highlight that the classical complexity graphs on the order of n power 3, where n is the size of the matrix X. To address this, they propose a quantum algorithm that can evaluate the gradient of the logarithm of the determinant in polylogarithmic times. So let us now see the constituent of this quantum algorithm of the gradient of logarithm determinant. The authors show that computing the derivative of the logarithm of the determinant is equivalent to summing the derivative of the eigenvalues divided by those eigenvalues. And the emphasizes the generality of this relation even when the eigenvalues are negative. So now the key question becomes how to how do we actually compute the eigenvalues and the derivative? To compute the eigenvalues, the author suggests using the random quantum block like those algorithm, which is described below. However, they also point out that there are other possible techniques and they should be considered when evaluating the final computational complexity. So now we know how to obtain the eigenvalues, but what about the derivative? For the derivative, the author relied on the quantum gradient algorithm. They show that at the end of this circuit, we obtain a quantum state that corresponds to the derivative of the function f. It is also interesting to note the similarity of this circuit with the quantum fast estimation circuit. So now we need to specify f. The point here is not to take the derivation of f, but the derivation of the eigenstate. To derive the eigenstate, the author used the quantum fast estimation technique combined with an operator that acts as a perturbation term. By differentiating the eigenvalues and applying a first-order series expansion, they obtain the derivative. Finally, just as in the previous circuit, they apply the inverse quantum Fourier transform to encode this derivation into the qubit M. So far, everything we have seen was about a single variable x eg that produces a corresponding variable y eg. At this stage, a quantum computer could in principle compute each element of the matrix in Y. However, doing this directly would require at least n square query to Oracle U. Now the authors propose something much more efficient. They show how to evaluate the expectation value of Y over a state phi using only one single query. To achieve this, they introduce a perturbation operator delta like this. With this approach, we can evaluate all the derivatives of an eigenvalues with respect to every x eigen, again with just one query. By By taking into account several factors, namely the number of eigenvectors, the precision epsilon in the quantum fast estimation step, the cost of the quantum Fourier transform, and the number of qubits required to implement the operator x plus L epsilon divided by n times delta. The authors derive the total complexity of their algorithms. They show that its scalar as this quantity. Okay, at this stage, the author have completely described the algorithm and their complexity. Now, let us take a look at some application. In kernel-based machine learning, we often need to compute matrix inverse, as see. In fact, in quantum kernel, one of the key elements of the prediction function is its parameters. The parameter vector, denoted by alpha, is obtained through this relation. As you can see, it requires the inversion of a matrix. This is where the quantum gradient logarithm determinant can be applied, since it can efficiently perform this inversion. Now, let us see an extension of a quantum gradient logarithm determinant. If the continuity of the quantum gradient logarithm determinant, the author introduced what they call the summate quantum gradient logarithm determinant. The idea is the following. Instead of initializing the circuit with a single eigenstate, we now initialize it with a superposition of the first star eigenstate. This also requires some adjustment in the definition of the oracle. Under these conditions, the algorithm produces a superposition of the derivative of all k eigenstates rather than just one. The author also presents some applications of the summate quantum gradient logarithm determinant in theoretical physics. For instance, it can be used to evaluate functional derivatives in quantum field theory or study the properties of Fermi liquids. Now, let's go to the conclusion and the outlook. In this paper, the author presents an algorithm designed to evaluate the derivative of the logarithmic determinant of a quantum on a quantum computer. They explain both the algorithms itself and its computational complexity. As announced, they prove that the complexity of the algorithm is polylogarithmic. Finally, they illustrate its usefulness by providing application in machine learning and in theoretical physics. Now, okay, the presentation of the paper is finished, so let me give you my opinion about this work. Uh, the approach is very rigorous, and the author provides proof for all theorems they present. The paper does not clearly distinguish between uh, inverting x, y, and computing the expectation values. In Also, it is unclear why the gradient of the logarithm determinant is emphasized, since the author showed that it's reduced to matrix inversions. The paper could have been framed as presenting a quantum algorithm for matrix inversion, with the gradient of the logarithm determinant as only an application. And for the end, the paper have some minor issues, like use two notation for eigenvalues, or not using bold font to indicate that delta is a matrix. The Those details, however, are easy to figure out. So that is all. So thank you for listening. I hope you enjoyed this video, and I will see you in the next one. Goodbye.